Well, we've generalized the flux passing through a potato. Now we want to get a little more specific and simple, actually, and look at the flux through a sphere as we're progressing toward formalizing Gauss's law. So here's a sphere, and we put a positive charge q inside of it, and as a result of that positive charge q, which at radius r, from the edge or surface of the large sphere that it's enclosed by, the electric field is radiating outward from this point charge, radiates outward, all right? And if we put a little area patch here on the sphere, we have the differential vector area pointing radially outward. That's going to be really, really nice. At the surface from charge q, the electric field size is kq over r squared, as we've already learned. That's just simply the electric field from a point charge at radius r. There it is, kq over r squared. Now, one beautiful thing about this sphere is that the E field is perpendicular to the surface at all points on the sphere. So there it is. There is the electric field vector, and it's also E perpendicular. Notice it's in the same direction as the differential vector area. So E perpendicular, what is it? Oh, it's just positive electric field E. So now that we consider that like a magnitude. The flux is the integral of E dot dA. Integrate all the E fields dotted with dA. Well, the E dot dA, they're directly multipliable because they're in the same direction. So it's just, the E is constant, and so it comes out. It's not varying on that surface. So we're going to integrate dA, and you know what the integral of dA is. It's simply the surface area of the sphere, which is 4 pi r squared. And so now, the flux through the surface, as a result of that little charge q inside, the flux through this entire surface is k q over r squared, k being 1 over 4 pi epsilon 0, right? So there's the electric field multiplied by the surface area, 4 pi r squared. Now, look at 4 pi r squared and 4 pi r squared. So what you're seeing now is the essential underlying connection between this proportionality constant k really being 1 over 4 pi epsilon 0. And you were wondering what this 4 pi was here for, what it was there for. Well, the electric flux exists in three-dimensional space. The permittivity is the ability of the electric field to exist in that three-dimensional space. And the electric field itself radiates outward in 3 dimensions, and so its size is associated with, as it hits the surface, all of it passes through a surface. When it gets out to here, it's all passing through this surface. And so the entire flux is passing through this surface of 4 pi r squared. So it's all connected together. The r squareds go away, pi's go away, 4 goes away. So this is why the proportionality constant really has the factor 1 over 4 pi in it. You see now that the flux through the surface of the sphere is really just the charge that it encloses divided by epsilon 0, having to do directly with the charge enclosed and the ability of the electric field to exist in the three-dimensional space diverging into this surface area, 4 pi r squared. It's independent of the radius because no matter what the radius is, all of the field flux passes through that surface area. If the radius is smaller, it's just a more intense electric field. So electric flux through a enclosed sphere like this is q over epsilon 0. A very simple and very important result. Now, just for clarity, perhaps a little bit redundant, about the effect of changing the radius of this sphere, let's consider the flux through a larger sphere. First of all, we have what we had before, q enclosed. Here's radius r. Calling it cap r right now. I'm not sure why. Actually, I do know why. Normally, small r is an intermediate radius through a finite volume, and to the edge is typically capital R. At least that's how I do it. In any case, we have this area element on there, differential area element. Now we're going to enclose this with a sphere of radius 2r, so twice the radius, differential area there. If we connect from the point charge lines through this differential area, we see that when we get to 2a, the electric field, first of all, at this location 2r, is going to only be a quarter the intensity at r because of the inverse square law. But the area element out here proportionately is 4 times the area element here. So what's 4 times differential? Well, it doesn't matter. Whatever that is, it's still 4 times as much in this analogy. And it's a good analogy because the area is quadrupled, but the intensity has been quartered, right? The E field is everywhere perpendicular to the surface, in this case of a sphere. So the flux through dA is the E field times dA. Same here. So really all the flux that passes through here has to pass through here as well. The intensity is less, the area is more. So the flux at this 2r location is a quarter times the E field, 4 times the area, which is the same thing as before, E dA. Over the entire surface, the flux then is Q over epsilon 0, which is always going to be the same no matter what the sphere size is. Now, let's just generalize this one more time and go over an irregular, like a potato-shaped surface, rather than the spherical surface. So, for the generalized surface, here's our strangely shaped object, and we're going to put a nice sphere inside of it with this, which is really, this sphere here is just really demarking a region of space, a spherical region of space with a Q inside of it. And really this is right now for mathematical analysis more than anything else. So here's our area patch on this surface, dA. And if we extend it out to the general surface way out here, you'll notice obviously got bigger. And moreover, the shape changed. It no longer has the same shape as this. Actually, if this is a perfectly spherical surface, I should have this perfectly shaped on these edges. But in any case, the fact that this is changing shape, this differential area, has something to do with our results. Well, here's a radius line going outward. And the normal vector is not in line with it because the shape of the surface is odd out here, and it's continuously varying. So this is our differential area. This is our electric field magnitude. And we have the perpendicular part, angle phi, with respect to the electric field. So that's E perpendicular. Now the flux passing through dA, this thing, I'm sorry, well, that's the same as the flux passing through the general surface dA. So both of the fluxes are the same. That's a given because all the flux passing through here has to go through this region of the surface. So E perpendicular is E cosine of phi, and that means that since this is going to be less than 1, then this has to be greater than E perpendicular. All right, that's pretty obvious, I guess. Now, here's the connection between these then. This flux through dA, if we project that out here to this generalized dA, if we had a spherical surface here, then the EDA, the flux through the spherical surface, would also be equal to the flux, the E times the area, through the general surface. And that's what this is, through the general surface. Now, but we have to multiply it by cosine of phi. Right? So if these are the same, again, if we had a spherical surface out here versus our actual surface, In the spherical surface, the shape would change, and that EDA of the spherical, which is more uniformly shaped than this, is this EDA times the cosine of phi. Now, the E's are the same. It's what it is. It's this value of electric field. So we can cross that out and write the differential area of the spherical surface, spherical out here, is the differential area of this general surface times the cosine of phi. And since cosine of phi is less than 1, this differential area of the general surface must be greater than the minimizing differential area of the spherical surface. Which means that there's more area here through which the flux can pass through, but it's not passing through normal to the surface. There's an angle between the E field and the normal. So, in any case, the flux through the spherical surface then is equal to the flux through the general surface. And the flux through the general surface is the integral of E dot dA. So now this integral takes on real importance, because if we integrate the E field and dot it with the dA, again, that's changing everywhere around on the surface. This differential area element is pretty complex because it's changing everywhere, or it could be at least, unlike the surface of a sphere where the dAs are all the same. And that's Q over epsilon 0. That's how we define the flux. And this little circle here denotes that we are integrating over the entire surface. That's what the circle on the integral sign means. Well, we've done all the work, so let's go ahead and formalize Gauss's law, which states the following: that for any charge distribution, the electric flux is equal to the closed integral of E dot dA, and that evaluates to Q enclosed over epsilon 0, where Q enclosed is the algebraic sum of all the charges that may add up to positive, negative, or 0. That's Gauss's law. Now in words, we could say it as follows: the total electric flux through a closed surface equals the net electric charge inside the surface divided by epsilon 0. And the reason this is so wonderful in our analysis is because we can take a simple geometry and put it around a charge distribution, determine what the electric field is at that surface, and then extend that to other regions of space around it, what the electric field there is as well. And we'll stick with the simple, because in complex situations like potatoes, we have a very complex integral that we can't do very simply at all. But this imaginary closed surface, I'm calling it an imaginary closed surface because it doesn't have to consist of anything. We're just placing a theoretical surface around this charge distribution and doing the analysis at that surface, which is called a Gaussian surface. Surprise, surprise. Now the practical forms that this flux relationship can take is that it's equal to the closed integral of E cosine of phi dA, which is closed integral of E perpendicular dA, which is closed integral of E dot dA. And in all cases, it is equal to the charge enclosed divided by epsilon 0. Let's consider the electric flux through each of the surfaces A, B, C, and D. Wow, that looks pretty complex, but really it's quite simple, because the flux through E, the electric flux through surface A, is simply Q over epsilon 0. It's Q enclosed over epsilon 0, but the only charge enclosed is Q. You'll notice the flux lines all going out of the surface. So that flux is Q over epsilon 0. Through B, the flux and charge enclosed is negative Q. So it's negative Q over epsilon 0. The flux through surface C is the charge enclosed over epsilon 0. Q minus Q, that's it. So that's 0. And finally, the flux through surface D. Well, it's not enclosed in any charge, so it's 0. Notice that this 5Q putting out basically its flux through areas, no problem, but given a surface like D, what goes in comes out. Same thing with these others. What goes in comes out. So it doesn't have any effect on the total flux through the surfaces shown here.